See that if let's say u in R is a unit, okay, u in R is a unit, then something which we can observe is that if R is a domain, if R is a domain, and R and S are in capital R, okay, we will use this fact a bit later. R and S are in capital R. Then the ideal generated by R is same as the ideal generated by S, if and only if S can be written as UR. Okay. Oh, we are giving you as a unit, right? But here the fact is that U can be any unit. U is some unit. Okay. Right. And this observation is pretty trivial because observe that if S is equals to UR, then that means S is some R multiple of small r. So S must be in the ideal generated by R. Right. On the other hand, you can observe that so yeah, so R S is in the ideal generated by R, and so this implies that the ideal generated by S is contained in the ideal generated by R, right? Because S, because if S is in R, then that would imply every alpha times S is in R for all alpha is in capital R. Because this is a ideal, right? The ideal generated by small r is an ideal, right? So that means that the ideal generated by S should be in R. The ideal generated by R, right? Because every element in the ideal generated by S is of this form, alpha times S, where alpha is some element from that being R. And similarly, since U is a unit, I can write R is equals to U inverse S, right? So the same statements follow to imply that the ideal generated by R must be the ideal generated by S, right? In other words, that the ideal generated by R must be exactly equal to the ideal generated by S. And the converse is also observed that if the ideal generated by R is equal to the ideal generated by S, then that implies there exists. Um, so I need to prove that S is equals to U times R for some unit, right? Yeah. So there exists some alpha and some beta in capital R, such that alpha times R is equals to beta times S, right? Okay. Let me not write it in this way. Let me rather write it in this way. Okay, this won't yield any important result. Okay, so this implies that small r is in the ideal generated by S, right? Since small r is in the ideal generated by itself. So that implies that there exists some alpha in capital R such that smaller can be written as alpha times S, right? We can do this, fine. But also S is in the ideal generated by R, since S is in the ideal generated by itself. So that implies that there exists some beta in R such that I can write S as beta times R, right? That implies R can be written as alpha times beta times R. That implies R times 1 minus alpha beta is equal to 0. Now, given that R is a domain, and obviously we are talking about the ideal R non-zero, right? What is the importance of talking about a zero ideal in any way? So that implies that R must be non-zero. Once R is non-zero, 1 minus alpha beta must be 0, right? But 1 minus alpha beta equal to 0 implies that alpha is a unit or beta is a unit, whatever, right? So that proves the claim immediately. Clear? Okay. Some other similar observations is you can observe further. So we had assumed U to be a unit, right? Observe that U times R must be equals to R then, right? Because what we have proved here is that if the ideal of R is equals to the ideal generated by S, then that is if and only if S is equals to U times R for some unit U. So that immediately proves this claim, right? If U is some fixed unit, then I can choose just S to be UR and it will prove it immediately, right? Therefore, the ideal generated by some unit multiple of an element is same as the ideal generated by that element itself. Got it? Okay. Now see, this immediately proves a very important fact, and you need to remember this important fact as well, that non-zero principal ideal, every non-zero principal ideal f of x in Rx, where R is a field, is generated by a monic polynomial. In other words, what I mean to say is that we had already claimed this fact, right? That if you have, if f is a field, then fx is a PID, right? A principal ideal domain. That is every ideal is a principal ideal. So that implies that if I is an ideal of fx, then there exists some polynomial px such that I is generated by this px. What this claim says is that I can choose this px to be monic. And why is it so? So let's go back to the structure of a polynomial. So the polynomial is structured as a n x to the power n plus a n minus 1 x to the power n minus 1, so on and so forth till a1 x plus a0, right? Where an is non-zero. But once an is non-zero and f is a field, that implies that an is a unit. Now we can write this polynomial as an times x to the power n plus an inverse an minus 1 x to the power n minus 1, so on and so forth till an inverse a1x plus a0 an inverse. Clear? Getting my point? And this is still a polynomial over fx. So if I choose this to be px and this was our f of x, then what we have written f of x is as some unit times p of x, right? N is a unit, so the ideal generated by this is same as the ideal generated by this, but unit times r, the ideal generated by your unit time and element is same as the ideal generated by that element. Got it? So every ideal in the PID of the polynomials over a field is generated by some monic polynomial, and it somewhat gives it in our hand that whenever we are going to talk about any ideal in a in the polynomial field in the polynomial ring over fields, then what we can do is that we can choose the generator to be a monic polynomial. Got my point? Fine. So in the last lecture we had introduced the notion of a GCD, if you will recall. Let us get back to our discussion now. Okay, we will use this fact in this lecture. That's why I just introduce this in some way. Okay, so we were talking about the GCD. Okay, so I'm not writing the definition anymore. So what was the GCD? So it is, by its literal sense, it is the greatest common divisor of two elements, of a pair of elements in any arbitrary ring, right? So we can in fact define it for any arbitrary ring, but the existence and non-existence is a different topic to discuss about. That is why we kept our discussion, because this course is as I said in the first lecture, that it is somewhat relevant to talking about an introduction to commutative algebra, commutative ring theory, and an introduction or a pathway to field theory. So our main focus was always commutative rings with unity and polynomial rings, right? So that is why in the previous lecture we discussed, the existence, or rather the definition of GCD over polynomial rings. We can prove later that if you have a unique factorization domain, that is an integral domain where there is an unique factorization of every element. If such a factorization exists, if any factorization exists, then the factorization must be unit up to and unit multiple, unique up to and unique multiple. In that case, GCD will always exist for any pair of elements. Okay, fine. So yeah, so how did we define the GCD? So we had said that if R is an integral domain specifically, and F and G are two elements from Rx, Rx is also an integral domain, we know it. Then the GCD of F and G was D if D divides F, D divides D, and if some element C divides F, C divides D, then C divides D. This was the basic definition, and there was an extra condition which we had said that D should be monic. Okay, D should be monic. We will see that D being monic will be sort of immediate once we talk about these over once we talk about polynomials over a PID, because there we will see that the GCD is basically the monic generator of the ideal generated by a pair of polynomials over the polynomial ring over fields. Okay, yeah. So let me just explain what I said. That we will see in a bit that if F and G come from the polynomial ring over a field, then the ideal generated by F and G should be the ideal generated by some monic polynomial, right? Because it's a PID, and we just saw that I can choose a generator which gives the principal ideal, and the generator can be chosen to be monic. So we will prove that D is actually the GCD of F and G. And you have seen in the previous lecture, I guess, that whenever I am trying to write a GCD, I am writing it like this, equal to 1 or equal to D, some sort of like that. So this notation of a GCD has somewhat arrived from here itself. Okay, that is the ideal generated by a pair of elements is same as the ideal generated by their GCD. Obviously, if it exists. Clear? Fine. Now let us get back to our discussion. Okay. Fine. Yeah. Let's see. Now observe a thing, that suppose a linear combination, some linear combination of say polynomials fx and gx in, okay, let us strictly be in the field, okay, is 1. Okay, what does this imply? That there exists a and b in fx such that ax fx plus bx dx is equals to 1. Then observe that then if d is a common divisor of f and g, then d divides this linear combination, right? A times fx plus bx times gx. So this implies that d must divide 1, but d divides 1 if and only if d is exactly equal to 1, right? Because after all we have chosen d to be a monic polynomial, and if d divides 1, then again you can go back to the division algorithm, and then you will obviously find that d must be exactly equal to 1. It's a very easy exercise, right? Or rather, even if you do not want to talk about d being exactly equal to 1, you can at least claim that d is a unit. Okay, you can at least claim that d is a unit. Okay, and in integers you would immediately say that d is a 1, but here you can claim that d is a unit. Why is it so? Because if d is a unit, then d inverse equal to 1, so that implies that d divides 1. right? Therefore, if two elements are such that their linear combination is 1, then their GCD must be a unit, right? Immediately the GCD must be a unit because GCD is after all a common divisor, right? Now let us see the following theorem, which is sort of a generalization of the Euclid's lemma of integers. Okay, it can be applied to polynomials over fields. Okay, so the statement is as follows: that let f be a field and let fx gx being fx with gx being a non-zero polynomial. Okay, then the GCD of fx. Okay, let me just apply the symbol once here. So the GCD of fx and gx equal to dx exists. Okay, what do we claim then from here immediately? That over a field, over the polynomials over a field, GCD will always exist, right? And it is a linear combination of fx and gx, right? Something which we have seen in integers, that the GCD of any two elements is a linear combination of those elements, right? So let us quickly prove this, and the proof is basically very simple. Okay. Observe that if I choose this ideal, I is equals to ax fx plus bx dx. Okay, for all ax and bx coming from fx. So this is basically the ideal generated by f and g. Now this should be a principal ideal. Why? Since f is a field, the polynomials over f forms a PID. Right? This we have seen previously. Right? Therefore, uh, there exists some monic polynomial. This also we have seen just a bit previously. That there exists a monic polynomial dx in fx such that the ideal generated by f and g is the ideal generated by d. Okay. What we claim is that therefore we claim d is the GCD of f and g. Okay. Now see, something which you can immediately observe is that d is a common divisor. Now, since the ideal generated by fg is exactly equal to the ideal generated by d, that implies that both the polynomials are in the ideal generated by themselves, which is equal to the ideal generated by d. Right? So that implies there exist some polynomials r and s in fx by the definition of the ideal generated by d. So that I can write f as d times r, I can write g times s, which implies that d must divide f and d must divide g. Clear? Got it? Okay. So one thing which we have observed is that d must be a common divisor of f and g. But is it the greatest common divisor? That is what we need to check now, right? Suppose c is some polynomial which divides f, c is some polynomial which also divides d. So I can write f as c times r, g as c times s, where r and s comes from fx, right? But then that implies, so what we can do from here? Okay. So observe that, therefore, what we can do immediately is that, so what we need to claim? We need to claim that I can write d as a linear combination, right? I need to claim that the linear combination, okay, right, fine. I now recall what we can do from here is that, see, one thing which we can immediately observe is that since d, the ideal generated by d is exactly equal to the ideal generated by f and g, okay, I should have mentioned it here in fact, that now d is also in the ideal generated by f and g, right? So that implies I can write d as a times f plus b times g, right? So therefore, d is equals to a times f plus b times g. This can be written as a times. So my f can be written as c times r plus b times c times s. So I can write it as uh, c times ar plus bs. Right? I can do this. So this implies that c divides d. Right? Therefore, d is a GCD. Right? Because c was an arbitrary common divisor of f and g, and we proved that c divides d as well. Got my point? Therefore, so this is the start point to observe. Therefore, over if every pair of polynomials has a GCD and the ideal generated by them is the ideal generated by the GCD. Got it? Fine. Now, observe this. Again, an observation. See, most of the things which we are studying in this course are very basically observation related, and that is exactly how mathematics should be studied, right? If you're only concerned about just your competitive exams or your college exams, then you might score good marks, but you won't be able to understand the concepts. Scoring good in exams is not always related to understanding things properly, at least nowadays, Okay, in previous days it was a bit different. Okay, but education was actually more fundamental than just giving exams. Fine. Okay, let us consider the ring fx mod I some ideal over fx. Okay. So now if since I is an ideal in fx, so this implies that I is generated by some monic polynomial px. Okay. Now suppose f is an element of the over the polynomials over this field such that fx and px are co-prime. Okay. Then by our previous result, therefore, there must exist polynomials s and t in fx such that sx times fx plus px times tx is equals to 1. But that implies sx fx plus px tx plus I must be equals to 1 plus I. Okay, if I take their modulo with respect to I, the ideal generated by px, yeah, so but the ideal is generated by px, so this must be an element in I, so this can be collapsed, right? So sx times fx plus I must be 1 plus I, but 1 plus I is the unit in fx modulo I or r modulo I for any ring, so this implies in fact, so I can write this as sx plus I times fx plus I is equals to 1 plus I. What does this imply? That f, or rather f plus I, is a unit in 1 plus I, sorry, in fx modulo I. Its inverse being this sx plus I, where s is the linear combination corresponding to f, right? Coefficient of the linear combination corresponding to f, right? Now, in fact, this converse can also be proven to be true. How? Suppose fx is a unit. Let fx plus I be a unit in R. R was fx modulo I. So that implies I can get hold of some gx plus I such that fx gx plus I is equals to 1 plus I. So this implies that fx gx minus 1, right? This should be equals to this should be 9, right? So I is the ideal generated by px. That implies that fx gx minus 1 should be some rx times px. So that implies that fx gx plus minus rx px is equal to 1. Got it? That implies that if d is the GCD of fx and px, then d must divide 1, right? But what can you say about the polynomial, the polynomials over fields about d, right? About the GCD, right? So this you can say that this implies that, or rather you can say this, right? Because that is the ideal generated by f and g must be the ideal generated by d, which is in fact some unit, so it is the ideal generated by 1. F and p, sorry, f and p. So what does this imply that? So f and p are co-prime, right? Oh, fine. So as we are on the course of doing just generalizations of whatever we see in case of integers, what we have seen till now, okay, let me just gist it up a bit. We have seen that the division properties of integers are sort of in 1-1 correspondence to the division properties in polynomials over a field. Okay, number of properties we have still seen yet of now actually say the same, and in fact the upcoming observations will claim it more and more. Okay, yeah, wait a minute. Okay. Yeah, so now we can prove the famous Euclid's lemma for primes in case of integers. Okay, recall in Z, if P is a prime and P divides a product of integers, then P divides any one of them, at least one of them, for some I in 1 to n, right? We can claim the same in polynomials as well. So this is sort of a corollary to the previous proposition. Okay, okay, yeah. So or rather, let me see the lemma. Okay, let it be a field. Okay, if px is in fx is irreducible and px divides q1x till qnx, then px divides qjx for some g. Again, what do we mean by irreducibility in a very layman sense? That you cannot write px as a product of two polynomials of lesser degree. Okay, take this definition up till now. We need only that much of a notion here. We will further develop the notions of irreducibility a bit later. For that, actually, in some sense, we need to introduce the notions of prime ideals and maximal ideals. We are going to do that most probably in the next lecture. Okay. So let's see this. So proof. Okay. See, what we can do is that we can prove the following, and then we can inductively just extend it. Okay. What we can prove is that if fx and gx are coprime, okay, and fx divides gx times hx, then fx must divide hx, right? Right. So what we are going to prove is that why are we assuming that fx and gx are coprime? Because we need to make sure that f does not divide g. So what are we actually doing here is that we are just taking this and reducing it to n equal to 2. Okay. So what we want to prove is that if px divides q1 q2, then px must divide either of them. So what we are doing is that px divides q2 if p does not divide q1, and we can just inductively extend it, right? There's nothing, because if I just take it to be true for some n, then I can assume it to be proving for qn plus 1 by grouping q1 till qn to be a specific polynomial and taking qn plus 1 to be the other polynomial, and then we can apply simply this proof itself, right? Okay. I will give you the hint towards the induction. You can write it rigorously, but let us prove it for now. Okay. Now see, if f and g are coprime, then what does this imply? That I can write this as some ax times fx plus bx times gx is equals to 1, right? So that implies that h is equals to h times a times f plus h times b times g, right? Further, observe, further, f divides gh. So this implies that I can write gh as f times k for some polynomial k. So that implies that h can be written as, so let me rearrange it a bit. So let me write it as a times fh plus b times gh, which is equals to a times fh plus b times fk, right? Yeah. So what we conclude from here is that h is equals to f times ah plus bk. This is also a polynomial over f. That means f divides h, right? So for the induction, what we can do, so what we have proved basically is that if p divides g1 g2, then p must divide g1 or p must divide g2, right? Okay. So now if I want to prove it like this, say g1 till gn and gn plus 1, okay, assuming it to be true for it being true till n, okay, then if p divides g1 till gn, then by the induction hypothesis p must divide gj for some 1 less than equals to j less than equals to n. Else we can do the same proof as we did here, because if it does not divide g1 till gn, since p is irreducible, so the gcd must be 1. Else by the base case itself, by the base case, p must divide gn plus 1, and we're done, right? Clear? Okay. Now once again, yeah, now, oof, yeah, fine, right? Yeah. Now let's observe the following corollary. Okay, and it actually, you know, wait a minute, wait a minute. Okay. There's a sort of an emergency. Wait a minute. Yeah. So let's continue. Right. So the corollary which we were about to state is that let f be a field and let fx and gx be some polynomials over f. Okay. Then I, which is the ideal generated by f and g, should exactly be equal to the ideal generated by d, where d is the GCD of f and g, right? Right? We can obviously claim this to be an immediate corollary, which we can observe. Fine. Okay. You always need to keep this in mind that d must be monic. You need to keep this in mind. Okay. Fine. Now furthermore recall that if you are in integers and let's say you have 2 and 3 to be two numbers, then there is a certain way of calculating the GCD of two numbers, which we call the long division method, right? And the famous term is the Euclide's algorithm, right? What did it say? It said that you need to keep dividing the larger number by the smaller number until you get a division with no remainder, right? For example, if I divide 3 by 2, what do I get? I get the quotient to be 1 and the remainder to be 1, right? Then what will I do? I will divide the first quotient with the first remainder, right? So this is 2, so this is 0, right? Therefore, the remainder, or rather the divisor, which is the last divisor, that will give me the GCD. The GCD of 2 and 3 is 1. For example, Let's see. Let's say another example. Let's say 12 and let's say let me think of some number. Let's say 12 and 36. Okay, or rather, let's say 12 and 38. Let's say. Okay, to find the GCD of 12 and 38. What we can do is that we can divide 38 by 12. So I get 12 is a 36. So this will give me 2. Next I divide 12 by this remainder. So I'll get 0, right? I'll get 6. So 12, so 0. Therefore 2 must be your GCD, right? So how is the division actually going? Okay, so suppose I take A and B in Z. Then I divide B by A to get A Q1 plus R1. Then I divide Q1 by R1. Sorry, I divide A by R1 to get A to be R1 times Q2 plus R2. Okay. So I'm dividing A by R1. So next I'll divide R1 by R2. So I'll get some R2 times Q3 plus R3. And I continue, right? I'll continue till I get, observe that Rn minus 1 equal to, what should I get? Rn minus 1 is equals to Rn Qn plus 1 plus Rn plus 1. And then I'll get at some point Rn is equals to Qn plus 2 times Rn plus 2. And it must end finitely, right? We will obviously reach this point because you can observe that R1 is less than A, then R2 is less than R1 is less than A. So basically this is an increasing, this basically gives me a decreasing sequence, right? So I have R1 which is less than A, which is less than greater than R2, which is greater than R3, so on and so forth, right? So we will reach the point Rn greater than Rn plus 1. But we know that Rn is bounded below by 0, right? So this process should terminate at some point, and here Rn, so Qn plus 2, so Rn plus 2 must exactly become 0, and in that case Rn plus 1 will give you the GCD, right? Because Rn plus 1 comes to be the greatest common divisor, right? See, this in fact comes out to be a GCD, right? Why? At least it becomes a common divisor, right? Because see, Rn plus 1 divides Rn, right? So if Rn plus 1 divides Rn, and if you reach here, so Rn minus 1 is equals to Rn times Qn plus 1 plus Rn plus 1, right? Now Rn plus 1 divides Rn. Am I writing it correctly? Yeah. So Rn plus 1 divides Rn. That means Rn plus 1 divides the right hand side. The right hand side is divisible by Rn plus 1. Therefore Rn plus 1 divides Rn minus 1. And similarly, if you get to Rn minus 2, you will see the right hand side will be divided by Rn plus 1. Since Rn plus 1 divides Rn minus 1 and Rn. And therefore you will conclude that Rn plus 1 divides Rn minus 2. So if you go on, you will see Rn plus 1 divides A and Rn plus 1 divides B as well. So it's indeed a common divisor. Why is it the greatest common divisor? Because you can see that Rn plus 1 is the greatest quotient. Rn plus 1 is the greatest quotient of A and B, right? Of dividing A and B by repeatedly the remainder, so on and so forth. I cannot go below it, right? Or, yeah, so this is one way of just thinking of it to be. Otherwise, you can think of it in this way as well, that if you take any other number which is a common divisor as well, then you can follow the same set of steps, and ultimately this Rn plus 1 itself will be that common divisor, right? Getting my point? Fine. So let us take this to be formal for polynomials, just for completeness. Okay. So theorem, the Euclide's algorithm for polynomials. Okay. So what does it says? It says that the GCD can be expressed constructively as a linear combination of A and B. Okay, how can you do this? Sorry, we are choosing F and G, let's say. Okay, over Fx. How can you do this? So let F be written as Q1 times G plus R1. Then from here I can write G to be Q2 times R1 plus R2. Okay, see, okay, let me write it in this way. Let me not be so fast. Okay, right, fine. So yeah, so then see, I can write F as Q1 times G plus R1, where the degree of R1 is less than the degree of G. I'm obviously assuming that this R1 is non-zero because I need to write at least a few steps to state this constructive algorithm. Then I can divide G by R1, so I can write this as Q2 times R1 plus R2, where the degree of R2 is less than the degree of R1. Right, here the degree is in correspondence with the value, the magnitude of the remainders in case of the integers, right? Then I can divide R1 by R2, so I can write R1 as Q3 times R2 plus R3, where the degree of R3 will be less than the degree of R2, and you continue it, right? Then you will get a point where Rn minus 2 is equals to Qn times Rn minus 1 plus Rn, where the degree of Rn is less than the degree of Rn minus 1. Rn minus 1 is equals to Qn plus 1 Rn plus Rn plus 1, where the degree of Rn plus 1 is less than the degree of Rn, And finally, we will get a step that Rn is equals to Qn plus 2 Rn plus 1, right? Such that the degree of, so yeah, here we have the remainder to be 0, right? Yeah. And this Rn plus 1 will be the GCD, right? Okay, right. Then Rn plus 1 itself is the GCD. And how can you take the linear combination in this case? See, you can write this Rn as Qn plus 1 times Qn plus 2 times Rn plus 1. So you can just do back substitution. Okay, you can just do back substitution and see it. Okay, it's a very easy thing to see. The back substitution is pretty easy. Writing it as a linear combination is a direct result of just back substitution. The thing to observe is the formal claim of this. Okay, so let's see the proof. The proof is actually very easy. See that D is equals to Rn plus 1 is the GCD after it is made monic in accordance with the definition, as firstly this iteration must stop inductively, must stop finitely, right? You can obviously have a justification of this just as we did in case of the integers. Also, this is the same thing, right? Rn plus 1 divides Rn, and then since Rn minus 1 is equals to Qn plus 1 times Rn plus 1, so this implies Rn plus 1 divides Rn minus 1. So this will again imply the same way of state Rn plus 1 divides Rn minus 2, so on and so forth. Rn plus 1 divides D, Rn plus 1 divides it. So it's a common divisor, right? Right. Again, if C is a common divisor, then what we do is that start from the list top to the list down, and then what we can observe is that C divides F and C divides D, right? So this implies C divides R1, right? Therefore this implies that C divides D and C divides R1, so this would imply C divides R2, so on and so forth, and then therefore continuing we will get C divides Rn plus 1. Got my point? And the GCD, as I said, it can be claimed just in the way that we have D is equals to Rn plus 1, which is equals to Rn minus 1 minus Q times Qn times Rn minus 1, right? So this implies that I can write D as, so I can replace what we can do from here. I can take here Rn minus 1 times 1 plus Qn plus 1, right? No, sorry, I missed a step, right? I can write D in this way, fine. Though then it's a linear combination of Rn minus 1 and Rn, right? Am I doing something wrong? Okay, this is Rn, sorry, Qn times Rn, I'm extremely sorry. This is Qn times Rn, right? Qn plus 1 times Rn, sorry. Rn minus 1 minus Qn plus 1 times Rn, right? So this implies that now Rn is equals to Rn minus 2 minus Qn times Rn plus 1, Rn minus 1, right? Then what I can do is that I can substitute D here, right? So my D can be written as Rn minus 1 minus Qn plus 1 times, so replace Rn by this, so this is Rn minus 2 minus Qn times Rn minus 1, and then it will be a linear combination of Rn minus 1 and Rn minus 2, and then you can just proceed in this way, right? Okay. Fine. Okay. Now let us observe some more properties of the GCD. Okay. Some more properties. For example, let F be a subfield of E. Okay, both are fields, and let fxgx be in f of x, okay, which is contained in E of x, right? Then the GCD of fg over f of x is same as the GCD of fg over E of x. After a few lectures, we will in fact see a generalization of this, where we can relate a similar statement over an integral domain and its fraction field. Correspondence between GCD of an integral domain and its fraction field. We will see it later. I mean polynomials over integral domains and its fraction field. Okay. So how can you prove this? See, suppose I write f of x as q of x times g of x plus r of x in E of x, right? So this is the division of fx in E of x, right? Such that the degree of r is less than the degree of g. So obviously I am not assuming r to be 0, fine, on a general note. But then I can also write f of x as some q of x times g of x plus r of x, such that degree of r is less than degree of g in, I can do this in f of x, right? Because small f and small g are in fx, so consequently it's in ex, right? But what we know is that polynomials over a field follow a unique division. right? They follow unique division. Therefore, by the uniqueness of division, and since small q and small r being elements of fx are also elements of ex, implies that q must be capital Q and r must be capital R, right? Thus, therefore, the proof is done. Why? By the Euclid's algorithm, right? Because this algorithmic division of Euclid, if it follows in the smaller field, polynomials over the smaller field, it will follow exactly in the same way as the polynomials over the larger field, and so we'll reach the same GCD whether we are in the smaller field or we are in the larger field. Got it? Okay, fine. Yeah. Now again, in correspondence to integers, what we can do is that define what we call the least common multiple. Least common multiple. Okay, and that definition is very easy to observe. Let f be a field, and fx and gx be in fx. Then the LCM of fg is defined to be let's lx in fx such that number one, that so gx divides lx, fx divides lx. Number two, if gx divides some mx, fx also divides some mx, or all this division is occurring in the polynomial over the field x, then lx must also divide mx. And three, obviously we will assume that lx is mode. Clear? And then we have a, so like we characterize the GCDs in terms of ideals generated by them, we can also do a sort of a same thing theorem. Let f be a field. Whenever we see f be a field, we know the polynomials over f is a PID, and fx dx is in fx. Then their LCM lx is the monic generator of the ideal generated by f intersection the ideal generated by d, right? Because we are in terms of common multiples, right? So why is this theorem, somewhat thought of this theorem? Because if I take a polynomial say p in f intersection g, then what does that mean? That means that p is in the ideal generated by f, that means f divides p, and then p is also in the ideal generated by g, so g divides p as well, right? Okay, this is a consequence. I think I haven't written it previously, but you can observe it somewhat, that some principal ideal is contained in the principal ideal generated by n, implies that n must divide n. Why? Because this means m is in there, m in here, and then this is equal to n if and only if n divides m and m divides n. In literal sense, we have seen that this happens whenever I can write m as a unit times n. Okay. Right. So therefore, any element in the intersection is a common multiple. Is a common multiple of f and g. Right. And we know that in some sense, the ideal generated by a certain element, this is the smallest ideal of the ring containing it, right? That is the reason why someone who or rather algebraist was motivated by this statement. And see, every theorem, it is not just accidental; it is a consequence of some deep thought or some deep observations, right? Fine. So first, since f is a field, fx is a PID, right? And the ideal, the intersection of both two ideals is always an ideal of f, right? That means that there exists some monic polynomial in fx, say lx, such that the intersection is generated by a, right? But just as we saw here that this element, that implies that this element L must be in the ideal generated by f and the ideal generated by g. That means that f must divide L and g must divide L. So in fact, L is a common multiple. L is a common multiple. So we need to show that if there is some other common multiple, then L must divide that multiple. So that is also pretty trivial, right? Now, if f divides some h, one second. Okay. So as we were saying, so if f divides some h and f divides some g, and g divides h, that implies that I can write h as some f times p and some g times q, right? So that means that h is in the ideal generated by f and h is in the ideal generated by g. So that means h is in the ideal generated by f intersection the ideal generated by g. That is the ideal generated by L. That means L must divide h. Right? Got it? Fine. Okay. Now let us move on to some important consequences of polynomial. We have discussed enough about GCD and LCM for now. If some situation arises, we will do it again. But now let us talk about roots of polynomials. Okay, in accordance with our thoughts, which we have done previously. Okay, sort of establishment of existence of roots. At most n number of roots are there, so on and so forth. Okay, fine. Those sort of statements. Okay, so let me start in the new page. Okay, so theorem. Let f of x be a polynomial and a be in f, then there exists a qx in fx such that f of x can be written as qx times x minus a plus f of a. Okay, what does it prove first? Let me see what is the posteriori of this statement. The posteriori is that given f of x in this, what we can conclude is that the remainder of fx when f is divided by the monic polynomial x minus a is f evaluated at a, right? And this is something which we have studied in our junior classes as the factor theorem, right? That is fx is a polynomial and I want to find the remainder of fx when it is divided by some linear factor, then the remainder is exactly the polynomial evaluated at the root of that factor. A is obviously the root of this factor, right? A, if I put x equal to a, it will become 0. And the proof is pretty simple. See, if I divide f by x minus a on dividing f by x minus a, there exists qx and rx in fx such that I can write f as q times x minus a plus r such that the degree of r is less than the degree of f, or r is equals to 0. Sorry, not degree of f, degree of x minus a. We are dividing by x minus a, right? But degree of x minus a is 1, right? But that implies that degree of r must be less than 1, which implies that degree of r must be 0. That means that r is a constant. R is a constant polynomial, right? Also, what is f of a? So f of a will become r at a, right? If I put just x equal to a, then this part becomes 0, so it becomes r at a. But r at x will equal to r at a because r is a constant polynomial, will be equal to f of a for every x, right? And hence I can write f of x as from qx times x minus a plus f of a. F of a in fact is 0, but that is not a matter of concern. If f of a is 0, that means that fx is divided by x minus a, right? That is our next corollary. Let f of x be a polynomial over f. Then we are all talking about in fields, right? This whole section is being talked about polynomials over fields. So is in f is the root of fx if and only if x minus a divides f. Okay. So the proof is again pretty simple. That is, if I divide f by x minus a, so I can write it as qx times x minus a plus f of a, right? So in that case, what we will have? So what is f of a, or rather, if a is a root of f of x, then what can we conclude? That f of a must be 0, right? Then that implies f of x is q of x times x minus a, which implies that x minus a divides f of x. And the converse is immediate, right? If x minus a divides f of x, then that implies I can write f of x as x minus a times g of x, right? In that case, we will evaluate that f of a is 0 by just putting x equal to a, right? Fine. So it's a very easy consequence. Okay. Fine. Now comes the important theorem. Right. Fine. So the theorem is as follows: that if f is a field and f of x in the over the field has degree n greater than or equal to 0, then f contains at most n roots of fx. It might contain none, right? It might contain none. For example, if I talk about this polynomial x square plus 1 in Rx, then Rx or rather R contains no root. R contains no root of x square plus 1 because we know that the root should be I plus or minus a, whatever, but I. Getting my point? Therefore, it might contain none, but if it contains, at most it can contain n. N is the degree of f. Okay, yeah. So n is the degree of f. Okay. So let's see the proof. The proof is a repeated, application of the previous corollary. That is, suppose suppose, or rather what we can, let me just give a sketch of the proof. See, let the roots of f of x be, let's say, a1 till an plus 1. Okay, for example, let's say it is the an plus 1. Okay, that is, we are assuming that let f contain n plus 1 distinct roots, of fx. Okay, then observe that fx is divisible by x minus a1 by the previous theorem times gx, g1x rather. Okay, also observe that since x minus ai is not equals to x minus aj for I not equal to j, and both are irreducible polynomials because they are just monic linear polynomials, so that means that their gcd must be just 1, right? Okay, now x minus a2 will divide fx, since a2 is also a root, but that means x minus a2 must divide x minus a1 times dx, but x minus a2 can't divide x minus a1, and also it is irreducible, so x minus a2 must divide gx. Therefore I can write f of x g1x, right? I took it to be g1x, so I can write it as x minus a1 times x minus a2 times some g2x, right? And I can continue doing this. So if I continue doing this, I will reach a point that is f of x, you can just induct on I, so I'll get x minus a1, x minus a2, so by inducting on I till x minus ai times gix, but we are over a field, so it's an integral domain, right? So at the last point I'll reach this part, right? X minus a1 times x minus a2 till x minus an plus 1 gn plus 1x, but the degree of s must be the summation of the degrees of these polynomials, so this should be, so yeah, so till here I'll have n plus 1 of these polynomials, right? So I will have it to be greater than n, right, which is a contradiction, right, because we have chosen it to be n. Therefore the degree must be, or rather the number of roots must be exactly equal to n plus 1, sorry, exactly equal to n if it exists, if it contains all of these, right? The right hand side is becoming greater than n. Getting my point? Now let me just give you a brief observation, and we will be using this, and this is a very introductory portion to what we call field theory, in fact, that is the evaluation polynomials. Okay, let f be a field, and consider the map, or rather we haven't claimed it yet, but we will see it later, that let k over f be a field extension. What do we mean by a field extension? Is nothing but that k is just a field containing f as a subfield, nothing else. Okay, that is, k and f are fields, and f in k is a subfield. Okay, then let phi be a map, let's say from f of x to k. Okay, what are we doing? So let phi a be it. So we are doing that phi of a. What does it does? It takes a polynomial and it simply evaluates it at a. So this is called the evaluation map at t. Okay, right? You can in fact restrict it to f itself. You can also restrict it to f itself, right? Yeah. And when we will be studying field theory, we will see that this evaluation map is extremely important. In fact, we had also made use of this evaluation map once. Recall that we had proved that zx mod ax is equal to z, is isomorphic to z. In fact, we had proved rx mod x is isomorphic to r. How did we do that? We had taken an evaluation map, right? And we evaluated it. So we had chosen a function phi from rx to r, where phi would map. Yeah. So the evaluation map at a, right? And we had proved that we will take a polynomial here and we will evaluate it to 0, and this will give me the isomorphism by the first isomorphism theorem. And then we will be having hold of the fact that irreducible ideals generated by irreducible elements are prime ideals, non-zero prime ideals are maximal ideals in certain structures of rings, and we will also prove in some sense that if P is a prime ideal, then the ring modulo this prime ideal, this becomes an integral domain. If M is a maximal ideal, we haven't defined it yet, we will see later, then R mod M is a field, then in those cases, these structures done by these evaluation maps and by the isomorphism theorem, repeated use of these, will give us certain field extensions which are very important, and these are just introductions to, these are introductory portions to field theory. Fine. Okay, so let this lecture be up till this much. In consequent lectures we will be coming up with definitions of finite fields. In fact, and then I guess before we will talk about prime ideas and maximum ideas, and then we will be moving on to finite fields. Okay. So meet you guys in the next lecture.